of these involves the measurement of the speed of light. In the 17th century, Galileo suggested a method for doing just that, but it turned out that light traveled too quickly. It seemed practically instantaneous in its travel time, and so the method didn't work. But a few decades after Galileo's death, Olaus Rømer used the eclipses of Jupiter's moons to get a fairly good estimate of the speed of light. It turns out to be about 186,000 miles a second, or about 300,000 kilometers per second. And in 1888, an experiment by Michelson and Morley showed that light really just doesn't behave quite as people had expected, at least as far as the law of additive speeds is concerned. Well, to see how the idea of additive speeds works, you can just think of a couple of automobiles, one traveling at 50 miles an hour, the other traveling at 55 miles an hour. Well, if they're traveling in the same direction, the one traveling 55 will overtake the slower vehicle. In fact, their relative speed will be 5 miles an hour. Now, if you turn the situation around so that the two vehicles are approaching each other, one at 50 and one at 55 miles an hour, well, then they'll hit head-on at a speed of 105 miles an hour. And it was thought that the same thing would work for light, that light should either add or subtract depending on the motion of the observer. And, of course, how quickly then and in what direction the Earth went around the Sun. That would affect the speed of light that we would measure for distant astronomical objects. To everyone's astonishment, the Michelson-Morley experiment showed that the speed of light was constant, no matter whether you went toward or away from the object that was giving off the light. Many other experiments have been performed since then, and they always come out the same. The speed of light is constant and the same no matter which direction you're going. Well, no matter how unexpected or unbelievable this idea was, it did cause objects traveling near the speed of light to act strangely. And the world came to understand in 1905 why these things were so through a theory developed by a 26-year-old clerk at the Swiss Patent Office, Albert Einstein.
Dr. Einstein based his special theory of relativity on several assumptions, which were, in turn, inspired by the results of contemporary experiments. He knew that the speed of light is not infinite. That is, light takes time to travel from one location to another. The Michelson-Morley experiment had shown that all observers measure the speed of light to be the same, no matter how fast either the observer or the source of light is traveling. Finally, Einstein reasoned that when individuals are in uniform relative motion, that is, neither one is changing speed or direction, it's impossible to determine who's moving and who's stationary.
Now, it's simple to understand the strange things that can happen to you or any object traveling at a velocity that's very close to the speed of light. Well, you can understand these things once you understand the principles of relativity. Now, to begin with, we have to think about uniform, regular motion. That's just motion in which you're traveling at a constant speed and a constant direction. And when you're in uniform, regular motion, and some other object is in uniform, regular motion, and you're comparing yourself to it, you can't really tell who's moving and who is still. In fact, the question's really kind of meaningless. It's like sitting in a train station with another train out your window. You probably notice that if the other train or your own starts pulling out, you can't really tell, for a moment at least, who's moving. That's because the trains don't take off with an abrupt jolt usually, just kind of gradually, so you don't feel any change. You really can't tell if it's you that's moving unless you look down at the tracks, which are another reference then for you to determine motion. But suppose you move these two trains out into the black void of space where you have no reference to work with, then all you can agree upon is the relative motion, the relative speed between the two trains. You can ask how much faster or slower one is going than the other, but you can't ask, in an absolute sense, how fast or how slow you're going.
Likewise, not even the speed of light can be used as a reference to determine an observer's absolute speed, because the speed of light is constant, no matter how fast the observer or the source is moving. So the only explanation for two observers who are moving at different speeds obtaining the same measurement would be if the measuring instruments themselves are affected as they approach the speed of light. And this is exactly what happens. Clocks slow down, rulers shorten, inertia increases.
Well, physically what happens is that if you take an object, let's say a proton, and you try to drive it up to very high speeds by, for example, accelerating it with electric fields, as you do in a particle accelerator. The faster it goes, the stronger its resistance to being pushed becomes. We say that its inertia becomes larger and larger. One often says that its mass gets bigger and bigger, but that's a way of describing that personally I don't like. I would just like to say that its inertia gets larger and larger. And as it approaches the speed of light, its inertia, its resistance to being pushed, becomes infinitely large. And so you put more and more energy into it. You drive it harder and harder, and it resists more and more. It gets more and more energy, but not more and more velocity.
An observer watching a spaceship traveling near the speed of light will see the ship's length shortened. Width and depth will remain unaffected. Only the dimension in the direction of the motion will appear compressed. The nearer the spaceship's relative motion is to the speed of light, the more contracted it will appear. However, the basic assumption of special relativity is that it's impossible for two observers in uniform relative motion to distinguish who's moving from who's stationary. From the point of view of the people in the spaceship, everything in the ship is normal. But looking out the window, the lengths of objects and the distance to their destination appear to be shortened. A third consequence of special relativity is that an observer watching an object pass by at nearly the speed of light will perceive time on that object as being slowed down. Again, the closer the object comes to the speed of light, the greater this time dilation effect will be. However, the fact that each person observes the same thing happening to the other creates an apparent paradox.
The twin paradox is an example of an apparent paradox which results from these peculiar predictions of special relativity. Suppose that you have two twins. One sits on the surface of the Earth, the other gets in a rocket ship and flies out to high speed in a rocket ship far away, say to the nearest other star, Alpha Centauri, explores the other star, gets back in the rocket ship, and flies back to Earth. Now, as seen from Earth, the clock or as measured, if you could actually do the measurements, the clock in the moving rocket ship that's carried by the man in that rocket ship will tick extra slow because that rocket ship is moving at high speed relative to Earth. And similarly, on the trip back, it will tick extra slow, and so you expect that when that clock gets back down here to Earth, that man who was in the rocket ship will have not aged as much as the man sitting back on Earth. But from another point of view, from the point of view of the man in the rocket ship, who talks about the clock sitting back on Earth, the clock on Earth is moving at high speed relative to the rocket ship as the rocket ship goes. And so it should be the one that runs slow. And so the twin back on Earth should be the man who is particularly young after the two come back together again. The resolution lies in special relativity, and relatively simply in special relativity. There's a fundamental difference between the clock, or the twin on Earth, and the one in the spacecraft. The one in the spacecraft accelerated out and accelerated back. The twin on Earth was not doing much acceleration at all. It turns out when you go through the details of special relativity and take that into account, the answer is clear and unequivocal. The twin that did the accelerating ages the least, and he may come back 20 years younger than his twin back on Earth.
One of the less popular consequences of special relativity, at least as far as science fiction consumers like myself are concerned, is that it's really impossible to accelerate an object to or beyond the speed of light. At least to do so would require an infinite amount of energy, and we have enough troubles as it is finding a finite amount of energy for our own current needs. Well, the obvious tricks toward getting up to the speed of light really don't work. One of the favorite examples, for instance, is taking a rocket ship and looking at it from the Earth. Well, we can look at those people in the ship, they can look at us back here, and we can agree on our relative motions between us. Say they're traveling at 95% the speed of light. It's no problem. But now we take another rocket ship and say it's also going at 95% the speed of light, but in the other direction. Well, then how fast is one going compared to the other? We might at first think, as Galileo would have answered, that of course the speed between the two rocket ships as they perceive each other is 190% the speed of light.
But in reality, this is not so. In fact, what we can find is that although speeds do increase, are additive in a sense, the greatest speed that we achieve in this fashion with the two 95% rockets is 99.9% the speed of light. We just can't break the barrier of the speed of light, no matter how we do it. Well, this is, of course, contrary to our common sense. It doesn't satisfy our normal expectations. But nature is under no obligation to obey our regular expectations or adhere to what we regard as common sense. Well, this theory is a good theory, but it would do our hearts even more good to have some experimental proof that it were so. And the best such proof might be found with the mu meson or muon.
Muons are tiny subatomic particles that can be created when the molecules in our upper atmosphere are bombarded by cosmic rays. They survive only about 2 microseconds, 2 millionths of a second, before disintegrating. So even though they travel at nearly the speed of light, they should only be able to travel about 1 kilometer before they cease to exist. Nevertheless, they actually travel about 10 kilometers between the region where they're formed and the surface of the Earth. Again, special relativity provides an explanation. From our point of view, time slows down for the muon. Its seconds are 50 times longer than they would be if it were not moving. Therefore, it exists long enough to reach the ground. The muon, however, has a different point of view. In its reference frame, it still exists for only 2 microseconds. But it perceives the lengths in the direction of its motion as being shortened. Consequently, from the muon's point of view, when it is created in the upper atmosphere, the surface of the Earth is less than 1 kilometer away. The observer and the muon both agree on the result, but their reasons for it are very different. These results supersede the need to travel faster than the speed of light.
Lots of people feel that somehow the speed of light is like the sound barrier, something that new technology will help us break. But science fiction notwithstanding, it is physically absolutely impossible for any material body to ever reach the speed of light. Nor should it need to, because the closer you go to the speed of light, the more your time slows down and the more all those distances shrink. Indeed, if you could ride on a light beam, and of course you cannot, but if you could, your clock would stop, all distances would shrink to 0. So that a photon, a light beam, is in a way you could consider it every place in the universe at the same time. In fact, you could travel to the most remote galaxy in a second if you could go close enough to the speed of light. So why should you want to exceed it? On the other hand, it doesn't follow that this is a practical means of interstellar travel, because the energies required to accelerate any appreciable mass to a speed near that of light are absolutely overwhelming. For a quick example, if you wanted to travel to a star 100 light years away and back in 40 years, you'd have to go 98% the speed of light. To accelerate to that speed of 98% the speed of light, say your rocket ship has a total mass of 20 tons. To do this with rocket propulsion would require some 200 times the entire output of energy used by man worldwide per year.
But Einstein wasn't entirely satisfied with his special theory of relativity. For 10 years, he labored to extend this theory from uniform relative motion to acceleration, including the effects of gravity. And in 1916, with the publication of his general theory of relativity, he succeeded. General relativity's underlying assumption is the principle of equivalence, which states that it's impossible to distinguish between the effects of gravity and an accelerated frame of reference. An example of a frame of reference where the effects of gravity disappear can be demonstrated with a variation of a physics experiment involving a cannon and a falling object. If we aim the cannon at the suspended bear, give the cannonball enough momentum to reach the bear, and drop the bear at the same time we fire the cannonball will always hit the bear, because both objects are falling at the same rate. From our non-accelerating point of view, we can see the curved path of the cannonball, But from the bear's accelerating point of view, the cannonball is always coming straight at it, as though there were no gravity at work. The principle of equivalence is perhaps best demonstrated in a small enclosed room, such as an elevator. Without looking outside, a person floating weightless in the elevator would not be able to tell whether the cable had broken and the elevator was in free fall, or whether the elevator was actually in empty space, far from any source of gravity such as the Earth. The downward acceleration of the elevator and all its contents in free fall actually eliminates the effect of gravity within it. But acceleration can also be used to create the effect of gravity where there is none. If the person were standing in the elevator, there would be no way for her to determine whether the elevator was motionless within the Earth's gravitational field, or whether it was accelerating through space at 1g. One might think that dropping an object would solve the mystery, but in fact, it doesn't. An object falls at a certain rate in the Earth's gravity. But if the person drops a ball in an elevator accelerating at 1g through space, the floor of the elevator rises to meet it at the same rate, just as it would have fallen on Earth.
So the principle of equivalence means that you can't distinguish a gravitational force from an acceleration. If you choose the right coordinate system, one that's accelerating, you can remove gravitation. Well, that can work locally in a Skylab or in a very local thing like an elevator. But to make it work for the whole Earth, where the direction of gravity is in different directions from different sides of the Earth, that's a more complicated problem. And to succeed in finding such a coordinate system, Einstein first had to introduce time. So you have to use 4 coordinates, 3 of space and 1 of time. But to use time as a coordinate is a very natural thing, because we never see instantaneously a snapshot of the real world. We always see different objects at different distances as they were at different times. In this room, I see the nearby objects slightly before, or as they were, I should say, slightly more recently than I see objects across the room. If I look outside at night, I see the moon as it was about a second ago. It's that far away. It takes light over a second to get to us. I see the sun as it was about 8 minutes ago. I see stars as they were years ago. So time is a very natural event, a coordinate. We don't see things where they are. We see events in space and time. And we need those 4 coordinates to describe them properly. In space-time, it is possible, and Einstein in his general theory of relativity showed how it's possible to find a coordinate system in which everything does move unaccelerated, as if there were no gravitation. However, this coordinate system must be warped in the presence of matter. Newton would say that the matter creates a gravitational field which produces forces that make the matter fall together. Einstein would say that the presence of matter warps space-time so that in this special coordinate system things move in a very natural, unaccelerated way.
Scientists have devised 3-dimensional embedding diagrams to illustrate the warping of 4-dimensional space-time near matter. The depth and steepness of the well is determined by the amount and concentration of mass. Einstein theorized that particles must travel in the shortest possible path in space-time. Away from the large concentrations of mass, a body would travel in a nearly straight line, but near massive objects, its path must curve. At the time Einstein made his predictions, he had no experimental evidence that his theories would work. He needed a test, and one was readily available. Problems with Newton's theory of gravity had begun to arise around the turn of the century. The most significant was the problem of the advance of Mercury's perihelion, its closest orbital point to the Sun. Most of this advance, which is shown greatly exaggerated in this scene, can be explained by the gravitational perturbations of the other planets. However, a minute amount, 43 seconds of arc per century, remained unexplained. Using general relativity, Einstein calculated that because of Mercury's nearness to the massive Sun and its highly elliptical orbit, which carries it periodically deeper into the Sun's gravity field, its orbit would be affected by curved space-time. He calculated that its perihelion would advance by approximately 43 additional seconds of arc per century. precisely the amount which was observed. The explanation of Mercury's orbit was extremely important, but that alone could not verify general relativity. The theory also predicted that a massive object would cause light passing near it to bend slightly. Einstein suggested that this aspect of the theory be tested during the next total solar eclipse, when stars near the sun could be seen and measured for a few minutes. The results of the experiments conducted at the solar eclipse of 1919 and the results of all subsequent eclipse experiments showed that starlight was bent around the sun very slightly, causing stars to be displaced outward in their apparent positions. The closer to the sun, the stronger this bending effect becomes. The effects are greatly exaggerated in this illustrated view from the Earth. This difficult and delicate experiment has been repeated more precisely in recent years. In the 1970s, it was performed using radio signals sent from the Mariner and Viking spacecrafts, which were orbiting Mars, when Mars was on the opposite side of the sun from the Earth. The results again showed that, as predicted by Einstein, radio waves, which are a form of electromagnetic radiation, traveled farther through the curved space-time created by the sun's mass. There's also a third test of general relativity, which involves gravitational redshift.
One of the consequences of relativity theory, or general relativity, is that there is a redshift, a shift of wavelengths of light caused by gravitation itself. Or another way of saying it is that light pulling away from the gravitational field has to do work, because in relativity we realize that light is pulled on by matter. Not only our material bodies, but also light is accelerated. So light has to do work pulling away from a star or any object with a gravitational attraction. But you can't slow light down. It always moves at the same speed. So the only way it can give up energy in spending this work is to change in wavelength.
This lengthening of wavelength has been measured in light emitted by dense white dwarf stars in binary systems. Atomic clocks, which were developed after Einstein's death, have also been used to detect this effect. However, there may be even more profound examples of gravitational redshift in space if the theoretically predicted black holes actually exist. The existence of these massive collapsed stars was not even imagined at the time of Newton.
Now, Newton's theory is a good theory of physics, but we discovered that it only works under certain limited conditions, the conditions in which we normally find ourselves. But Einstein's theory was more general, more universal than Newton's theory of gravitation. It went beyond it. But Einstein's theory of relativity has its limits too, and to extend beyond these limits requires a leap of imagination no less great than that needed by Einstein to go beyond Newton.
A violent nuclear furnace spews forth millions of tons of energy every second, the equivalent of some 500 billion horsepower.
Well, throughout history, the basic problem in determining the source of the sun's energy has been to find a source that's able to produce that much energy for that long a time without consuming most of the sun in the process. Now, of course, we're able to look at sunlight with solar telescopes like these, but understanding the source of that light is another matter entirely. We need to have a theory which explains and agrees with the evidence. Now, the sun has been shining for about 4.5 billion years, and that means that any theory, any explanation of the sun's energy is going to have to keep the sun shining for that long a time at least. Now, there have been lots of ideas proposed to explain how the sun shines, but most of them have failed, largely because they can't keep the sun shining long enough. Well, for instance, in the 5th century BC, Socrates simply proposed that the sun was a red-hot stone. Unfortunately, it would simply cool off much too fast, so that doesn't work. At about the same time, Pythagoras suggested that the sun shines by reflected light. It doesn't give off light of its own, he said. Well, this simply moves the problem of the energy of the sun elsewhere, to the so-called Great Central Fire, which was always on the opposite side of the Earth. Or you could imagine that the sun is just a lump of burning coal. Well, you've got 2 times 10 to the 33rd grams of sun to burn at a rate of 4 times 10 to the 33rd ergs per second. That's just the energy output of the sun. And doing that with coal, burning coal at that rate, only allows the sun to last a few thousand years. So that explanation obviously can't work either. But in 1905, Albert Einstein was able to suggest a relationship between mass and energy, E equals mc squared. And this would permit a small amount of matter to produce a great amount of energy. Well, in 1938, Hans Bethe and Charles Critchfield were able to show that thermonuclear fusion could make E equals mc squared work. They were able to find a reaction that could explain what we see, the evidence, in terms of the known laws of physics. Since 1938, we've refined the reactions, but we believe the basics are still the same. Hydrogen is transformed in a process which produces great amounts of energy.
A spectrogram of the sun shows the 2 simplest and lightest elements, hydrogen and helium. The word helium